Hi everyone, welcome to Edison Bob. Today we talk about Polkadot, Blockspace over blockchains part 2. This is the second part of the video on Robert Habermeier's article on Blockspace. If you haven't seen the first one, please make sure to do it because this is basically just a continuation where we continue on reading. First video was 55 minutes. I expect today's video to be a bit shorter, but we're going to cover 2 chapters and the conclusion of the article. Okay, so let's go on. Polkadot, a block space-centric design. So we closed off, and basically the first part of the video was the general introduction to the concept of block space. What is block space and what are the characteristics of block space and a few of the implications. And now Robert goes into the implications for Polkadot. Polkadot's consensus system is, at its heart, an efficient and flexible block space generator. Like modern CPUs, the Polkadot network is a multi-threaded machine. This system is based around a single primitive, the execution core. Okay, so multi-threaded machine basically means it works like a modern CPU. So it does not have a single thread, it does not have a single line of execution where a program can run, but it's multi-threaded. So multiple programs can run at the same time and can do so efficiently, which basically is the parachains. So each parachain, as he will highlight now, is basically running in its own core. This system is based around a single primitive, the execution core. Each core can execute one block from a state machine at a time. And a state machine is a blockchain, right? So, in simple terms, it's a blockchain. But basically, the state machine is the thing that powers the blockchain, and each execution core can execute one block at a time. The network makes use of its resources in the form of validators and bonded stake to expose the maximum number of cores at any time. So oftentimes you see this discussion of what is the transactions per second. And in the context of this discussion, it basically means the network has resources available. For example, the validators. So Kusama has, I think, almost 1,000 validators. Polkadot has a few hundred, and this is the resources that the network has available to generate block space and the bonded stake. And so it can use those resources, it can allocate different validators to the validation and execution of those different cores, those different parachains. So each parachain essentially gets its own execution core. And the idea is to maximize the number of cores, to maximize the number of blocks created and maximize the generation of good, high quality block space. Due to the efficiency gains of Polkadot's architecture, Polkadot's validators are able to transform the real resources they consume into more block space than simply by running more standalone blockchains with the same staked value. Yeah, so this is basically an argument for efficiency. Shared security on its own is not enough to build an effective block space producer. Shared security guarantees homogeneous quality of block space. It must be coupled with a scaling mechanism to guarantee supply. Okay, so we have the quality, which is determined by the stake, by the shared security, but now he's talking about how can we make this thing scale, which is basically the debate of, okay, of course you can throw in a lot of stake into the relay chain, but if it's just a relay chain producing blocks, you won't get the same throughput. And so this is where parachains come in, which basically make the thing much more scalable. As a block space producer, Polkadot does its best by opening up its services to the maximum number of users possible. Because Polkadot uses WebAssembly and a virtual machine architecture, Polkadot blockchains don't need to convince validators to run their software. Like smart contracts, the only requirement is to post code on chain and acquire block space. Okay, so blockchains don't need to convince validators to run their software. You have this in also other modern third generation ecosystems like Cosmos and I think Avalanche, if I'm correct, where, so at least for Avalanche I think so, because you basically have to convince the validators to also provide security for your project. There's also EigenLayer, where basically each project has to convince the stakers to also stake for them, and so on and so on. In the case of Polkadot, it is different because the protocol itself, the Polkadot protocol itself, describes the mechanism how you can acquire block space by basically winning a slot auction. And when you have won the slot auction, you are validated by the whole validation set. So the whole validator set is making sure, or the whole relay chain is making sure that you get included. So the only requirement is to post code on-chain, the code of the runtime, so basically the Parachain runtime code, the state transition function, and acquire block space. Getting a slot so that you have a continual subscription of block space over an extended amount of time. Polkadot validators have no choice in which blockchain they are required to work on at any given moment. The only thing that matters to them is which core they are assigned to at any time, and the corresponding blockchain scheduled on that core. Yeah, so I was already describing this a few sentences ago. Each validator gets assigned a core. Each core has a parachain on it. The parachains could also swap from time to time, so this is decoupled. This is no longer the problem of the validator. Validator just looks at the core, takes the work that is to be done, and executes the work. And so you have a nice decoupling of these responsibilities, and each component of the protocol can optimize for its own thing. Polkadot validators are pure service providers. They are not opinionated. They work on what the market tells them to work on. Purchasers of block space in Polkadot have a guarantee that validators will hold up their end of the bargain without any human intervention. And validators which do not do so will be missing out on rewards. Okay, so it's basically describing the incentives and also how the protocol enforces this. So the protocol enforces this by making it part of the core relationship of validators to the network, that they just validate the work that is given to them by the cores. It's fair to consider Polkadot a roll-up protocol. Yeah, so this is a discussion that's being had. Is it a roll-up protocol? However, and what does roll-up protocol mean? It means that so when Polkadot is a layer 0 chain and every parachain on top is a layer 1 chain, what does it mean technically? It means that the parachains are producing blocks, and then the summary of what the block does is created, which is sort of a digest or a hash or something, which basically rolls up the state into a much more compact piece of information, and this then gets validated by the relay chain. And this is what the shared security means. The parachain is producing much more information, but it condenses the information down to a rollup, and this gets validated by the relay chain, and thereby is committed, is finalized, and is secured. And so it's fair to consider Polkadot a rollup protocol. This is, for example, also what Ethereum is going to likely with their sharding, where they are basically saying any layer 2 is rolling up into the Ethereum and settling on Ethereum. However, unlike rollup protocols based on smart contract systems, the rollups are enshrined in the base layer logic via execution cores. So the execution cores are what rolling it up. When rollups are built on top of a smart contract layer, the system to some extent devolves into every rollup for itself, as they compete for gas, validators, inclusion, and scheduling. Okay, this is very loaded. We will unpack it, but let me read the sentence. The transactive gas-based block space at the base layer is not best suited to allocating block space to rollups. In order to provide consistent guarantees about scheduling, security, and supply, we are building a specific system which is modular, where modularity counts at the application layer. Okay, so what is he describing here? A problem that you might get on Ethereum when you have all of those layer 2s is that the layer 2s need to roll up onto the layer 1, onto Ethereum, to settle what is there to settle, to basically secure and imprint the information on the layer 1 chain. Now the problem is, if gas is becoming more expensive, or if they are becoming competitive, or maybe becoming hostile to each other, and MEV might be a reason here also, is that they could fight for actually getting included in the core layer, in the lowest layer. And so there is no guarantee on Ethereum that if you have a layer 2 that you will get rolled up into layer 1. You have to actually bid for inclusion in the block. And so this can become very competitive, and it can produce a problem at any point in the future. So when rollups are built on top of smart contract layer, basically what we see on Ethereum, the system to some extent devolves into every rollup for itself. They have to fight and compete for gas, for validators, for inclusion, and for scheduling. Scheduling also means, do they have a continual inclusion? The transactive gas-based block space at the base layer is not best suited to allocating block space to rollups. Yeah? And so basically it is making the argument now that Polkadot can provide consistent guarantees, which is also another good argument for good quality block space, about scheduling, security, and supply. Okay. The architectural distinction between the execution cores and the actual blockchains or state machines which run upon them is of crucial importance. We see little value in maximizing the number of blockchains, obviously. This is only a proxy for what matters most: maximizing secure block space. Execution cores are the engine of block space production, and the scheduling rights to those cores upon a design space for block space allocation products. Okay, so he's summarizing this chapter here and is going into the next chapter, and this will be about mechanisms for allocating block space. It's a real interesting and mind-blowing chapter. So let's get into this. So to summarize this, he's basically making this argument for creating an architecture that is organized around cores, with the idea that cores can maximize the good block space that is produced. But now it comes to how can we allocate the block space that is generated in the most efficient way possible. Okay, mechanisms for allocating block space. Efficient block space allocation is critical. Usage patterns of blockchains are not consistent. Blockchains experience periods of heavy load and congestion, as well as periods of underutilization and emptiness. You can see this that most days Ethereum, you can get your transaction through okay. And then there are days when there is a new token coming out or a new NFT collection coming out, and suddenly everyone tries to get that NFT collection, and it clogs up the system for everyone. Which can be bad for DeFi, because for DeFi you want to have a continual, consistent access to the system. On the one hand, applications should be able to adapt to periods of heavy load. On the other hand, applications should not pay for block space they are not using. The product design space here is underexplored, but Polkadot's architecture is uniquely amenable to improving the market's offering. Okay, so we are having this argument of sometimes products use too much block space, sometimes too little. Can we bring in more efficiency? One parallel for thinking about the design of block space allocation products is the cloud computing market. Cloud computing business models often have two key features: reserved instances and spot instances. Reserved instances are cheaper but guaranteed for a prolonged period of time. So this basically means a computer that is just reserved for you. No. No, yeah, it's right like this. So reserved instance is cheaper, but you basically reserve it for a whole month, for a whole year. You get a cheaper price, and it's dedicated for you. But if you utilize it or not is up to you. Spot instances are more costly. You buy them on the spot when you need them. Are more costly, available on demand, and ephemeral. They come and they go. Applications with predictable load will save money by purchasing reserved instances, but can scale to meet demand without service outages by utilizing spot instances. So basically you have a baseline assumption of how much resources you need, and then for everything that you need at peak times, you just allocated it on the spot. However, reserved instances also represent a commitment. The application operator is wasting money if real demand for the application falls below the reserved supply of cloud compute resources. Okay, interesting analogy. Let's make this concrete. Long-term slots, parachain slots, are the only current mechanism for allocating Polkadot's execution cores. These are akin to reserved instances, allocated either by governance or by slot auctions. The winners earn a dedicated execution core for a predetermined time of 6, 12, 18, or 24 months. Okay, so any parachain that wins a slot basically wins a subscription or a reserved instance of Blockspace, of an execution core that generates Blockspace over the period that is over a fixed period. Parathreads, which we first introduced as a concept in 2019, are pay-as-you-go blockchains. So it's sort of similar to spot instances. Parathreads are like spot instances. Our current thinking is for this spot price to be set using an optimal controller. In simple terms, the price will go up when the cores exposed by Polkadot for Parathreads are saturated, and the price will go down when there are empty cores. So some cores will be reserved for spot buying of Blockspace, and the price will be determined by how much in demand they are. This is just one further example of how Blockspace can be allocated. Okay, now it gets wild. We can take this concept of allocating block execution cores further. Polkadot's architecture is such that a single chain can have multiple cores allocated to it simultaneously. Imagine a blockchain that instead of advancing by one block at a time, advances by 2 or 3. This is possible and is due to particularities of Polkadot's design that allow for validation of sequential state transitions in parallel. In practical terms, the number of cores a chain can efficiently occupy is limited only by the number of cores it can acquire at a time and the rate at which the chain can produce blocks. Which basically means if you can find a sufficient design and implementation, you can increase your throughput. We expect that as this market matures, there will be a wave of innovation in block generation for Polkadot chains to maximize the utility of this feature. We expect that even chains with a simple sequential block offering method, such as the currently available, would be able to make good use of 2 or 3 cores. Yeah. So imagine you have a parachain that sees heavy use, and you just are filling block by block, and you have more demand than you can fill blocks. Users would have to wait, or you acquire more cores and use them at the same time. As an example of how multiple cores might be used by a single chain, we could introduce another type of Blockspace allocation product, short-term auctions. These auctions would fall somewhere between pure spot allocation and long-term reserved allocation. It is certainly possible to design an auction mechanism for allocating slots for short durations, such as 1 hour, 1 day, or 1 month. This could be used for something I've been terming parachain boost, the ability for blockchains to expand their throughput during periods of heavy load, like a highway that gets wider during rush hour. So the idea here is, let's say you have a constant use, or you have your reserved allocation of Blockspace, and then imagine you're a DeFi chain and you launch a new token and suddenly there is more interest, or you launch a new pair, a new product. Initially you have this burst of activity. For this burst of activity, you can allocate more execution cores. You can rent more block space for a determined amount of time. And for the moment, this is being called Parachain Boost. Furthermore, by changing our perspective from blockchain-centric to block space-centric, it becomes clear that there is no reason a blockchain or state machine should run forever. Ephemeral blockchains are an interesting use case. Ephemeral, so a blockchain that just comes, stays for the amount of time it is needed, and then it goes. It's an interesting use case, I believe, is highly underexplored. Longer running processes should be able to offload their computations or protocols to short-lived chains, just like programs running on a PC can offload computations or work to background threads. So if there is any complex execution that takes quite some time, it could be offloaded to an execution core where just this part of the application is uploaded to and executed. One final avenue we can pursue for execution core allocation is the ability to transfer claims on execution core. So you have a claim on time on the execution core. And you could create a secondary market for Polkadot Blockspace. Chains will be able to trade extra capacity with each other and act as resellers of Blockspace. So imagine you have won a slot auction for 24 months and now you're reselling this in different time slots on a secondary market. Chains experiencing lower or higher demand than anticipated will be able to adapt accordingly, or perhaps even speculate on future demand of Blockspace. So, in summary, reframing the meaning of blockchain. In my opinion, in Robert's opinion, the blockchain ecosystem has been thinking too small about the multi-chain world. And I agree. I think this article is eye-opening. Blockchains that start and run indefinitely with a steady pulse are an evidently inefficient mechanism. The multi-chain of tomorrow consists of blockchains that scale and shrink on demand. It contains ephemeral chains spawned by on-chain factories, spun up by contracts and imbued with automated purpose, to complete their work a few hours later and disappear. Our goal in Web3 is not to maximize the number of blockchains. Maximizing the number of blockchains is something I would state explicitly as a non-goal, as it primarily benefits validator cartels seeking to extract value. Our goal in Web3 is to maximize the amount of block space that exists and ensure it is allocated to the state machines which need it the most at any time. A constant generation and allocation of global consensus resources to those who need it the most. An enterprise without waste. In other words, the most effective block space producer in the world. I think Robert has a talent for concluding chapters. This is really nice ending here. And yeah, here you see some nods to Fabian Gompf, Pranay Mohan, Björn Wagner, and Gavin Wood for review, edits, and discussion. Yeah, so I hope you enjoyed this article. I really took a lot out of it, and I think there is just a lot of opportunity to discuss this with people, to look at other blockchains in this context. How does Bitcoin compare in this sense? How does Ethereum compare in this sense? Cosmos, Avalanche, Solana, Cardano. You could look at any offering and start looking through the lens of Blockspace. And I think there is a lot to learn from this, and grow our knowledge and insight into Blockspace and digital ledgers. Okay, I hope you enjoyed the video for today. And yeah, 24 minutes. If you enjoyed the video for today, make sure to subscribe to Edison Bob on YouTube and also on Twitter. I'm at Edison Bob. Yeah, see you next time.